Okay, so let's start with the modulation. What is modulation? Because the communication start with the topic modulation. I am not taking the part of the signals and system. So we will start from the modulation. What is modulation? So modulation is the process where the two signals are involved. Okay, so one is the carrier signal and another is the message signal. So modulation is the process in which the characteristics of one waveform, which is known as carrier waveform, the characteristics of the carrier varies in accordance with the characteristics of another waveform, which is your message signal. So we have the two signals and we have to change the characteristics of carrier signal according to your message signal, because the carrier signal has three parameters like amplitude, frequency and phase, and the message can be anything. It can be video, it can be audio, it can be in the data form, it can be image form. So according to this image or according to this message signal, the carrier signal should change its characteristics. Okay, so this is the first definition of the modulation. The another definition of the modulation is nothing but the modulation translates a low frequency signal into high frequency signal. Whenever you perform the modulation, a low frequency signal will transform into high frequency signal, and that is why we actually modulate, because we want to increase the frequency so that there are many benefits of increasing the frequency, shifting your message signal into higher frequency. So in simple words, if I say modulation is nothing but the frequency translation. So modulation is a frequency translation technique also, and modulation also convert the low pass signal into a band pass signal. Whenever you perform the modulation, the low frequency signal, low pass signal will shift to the higher frequency signal, and that will be called as the band pass signal. Okay. A random variable, you have two questions. There will be a from the random variable. Okay, Sagar, there will be definitely two questions from the random variable. So whatever your doubt with that, just put in the comment box so that I will answer your doubts also in between the session. So what are the need of modulation? The first need is the modulation reduces the height of antenna. As you increase the frequency, the wavelength get reduced, and the height of antenna is directly proportional to the wavelength. So if the wavelength reduces, the height of the antenna also reduces. Good evening. Good evening, Ravi. So this is the first, and the second need is to avoid the mixing of the signal. When you modulate, it shift to some higher frequency, and by assigning the different carrier frequency to the different user, you can isolate your message signals. Okay, you can isolate your message signal, and it will avoid your mixing of signal. It also increases the range of frequency. Okay. The fourth one is modulation allows adjustment of the bandwidth. Modulation allows multiplexing of the signal. Modulation improves the quality of reception. So these are the need of the modulation. That is why we perform modulation. So this is the very basic of the amplitude modulation. Now coming to the modulation technique, how do we perform the modulation? Actually, to perform the modulation, we always multiply our low frequency signal into high frequency signal. So we have to multiply the low frequency signal, which is usually our message signal, and the high frequency signal are usually carrier signal. So if you multiply these two, and if you suppose give input to the modulator, you get the modulated signal, which is a high frequency signal, or which can also be known as band pass signal. So you get either high frequency signal, or you can also say it as a band pass signal. So you will get the band pass signal or a modulated signal. So to perform the modulation, you have to multiply the signal which you want to modulate with the high frequency. Okay. Hello, good evening, Malati. Now, what is the time domain representation of amplitude modulated signal? So before going to the time domain, let's define the amplitude modulation. If the amplitude of the carrier signal varies, okay, how do you define amplitude modulation? If the amplitude of the carrier signal varies according to your modulating signal, instantaneous value of the modulating signal keeping the other parameter constant, we call it as a amplitude modulation. The difference between the baseband and the band pass. So the baseband means the low frequency signal, okay, and the band pass means is a frequency which is centered at high frequency. So let me take this question, okay. So let me draw here the difference between the baseband and the band pass. Okay, let's take this. This is the low frequency signal which is also known as baseband signal. All the message signals are baseband signals only. And what is the band pass signal? When you will shift this message signal into some higher frequency, it will become the band pass. So this is how you represent. Okay. So this is the baseband signal. This is your baseband signal which has some highest frequency, that is band limited to some frequency FM, and having the lowest frequency minus FM. This is centered about origin. Baseband signals are centered about origin and band pass signals are centered about some high frequency. It is centered about some high frequency. Band pass signals are centered about high frequency. Okay, centered about high frequency, and it is centered about origin. Okay, okay, round tube, I think it is clear. Yes. So now we are in the time domain expression of the amplitude modulated signal. So the time domain representation of amplitude modulated signal is given by this: S of t is equal to AC 1 plus kmt cos omega ct. Okay, AC 1 plus kmt cos omega ct, and where k is known as the amplitude sensitivity of the modulator, whose unit is volt inverse. Okay, so this volt inverse is here. Okay, now the next is time domain expression. If we want to define the modulation index, suppose you want to define the modulation index or depth of modulation, it is the measure of the extent to which modulating signal modulates the carrier signal. Okay, so how much depth of modulation is there in the carrier, because the carrier is going to modulate. So how much depth you are modulating is measured by the modulation index, and the modulation index is given by K into K is the amplitude sensitivity and maximum value of your message signal. K into maximum value of your message signal. And if the message signal is single tone sinusoid, so message signal is single tone sinusoid, that means mt is equal to am cos omega mt. Single tone means if your message signal is having only one frequency component, then it is known as single tone, and it is having only one frequency, that is your FM. Okay. Now, if this is the message signal, then modulation index is K into AM, and modulation index is also defined sometimes by AM by AC if the K is not given. If in the exam suppose K is not given, then you can take the modulation index as AM upon AC. Okay, if K is not given, then you can calculate the modulation index by AM upon AC. Next is, for a single tone sinusoidal message signal, what will be the envelope? The envelope is AC 1 plus MA cos omega MT. Okay, the AC 1 plus KAMT cos omega CT was your AM signal expression. So if you substitute the message signal here, then this part is nothing but the envelope. Leaving the cos term, the remaining part will be called as the envelope. So envelope is AC 1 plus MA cos omega MT. The maximum value of envelope will depend on the value of cos. The value of cos is 1. So this is AC 1 plus MA. This is your first equation, and minimum value is AC 1 minus MA. So this is second equation. So if you add these two, you will get the amplitude of the carrier. So the amplitude of the carrier is given by average value of maximum and minimum value of envelope. Modulation index is given by Emax. Modulation index is given by Emax minus Emin divided by Emax plus Emin. So these two are the important formula. The carrier amplitude you can calculate directly from the envelope. The modulation index can also be calculated directly from the maximum and minimum value of envelope. And even though the message signal can also be calculated, so message signal amplitude you can calculate by subtracting the maximum and minimum value of envelope and then divided by 2. So this is the message signal amplitude. So the use of envelope to calculate the carrier amplitude as well as modulation index. So these two are very important formulas. Next, coming to the time domain representation. So at t equal to 0, suppose at t equal to 0, we have the message signal applied. So before the t equal to 0, we have the carrier signal as it is, because we have not applied message signal yet. So when you will not apply message signal in the amplitude modulator, it will become the pure carrier signal. So carrier signal when no modulation. Carrier signal when no modulation means AC cos omega CT. Carrier signal without modulation is AC cos omega CT, and AC cos omega CT will have the amplitude between plus AC and minus AC. So that is why here you have the amplitude between plus AC and minus AC, and this is called as unmodulated carrier. This is called as unmodulated carrier. Yes, so next question is, yes, good evening Vijayalakshmi. How many marks can I get only preparation of analog communication? So Naveen, if you are only preparing analog communication, then you can expect 2 questions from the analog communication. That means around 3 to 4 marks you can expect. Okay, so 3 to 4 marks can be prepared by only preparing the analog communication. In the analog communication, I am not including the random variable and random process. Okay, so in analog communication, I am saying only about the amplitude modulation and the angle modulation and the receiver. These 3 topics, if you are preparing, then you can expect 3 to 4 marks. Okay, if you prepare well enough, and suppose you are not prepared well, then these marks you can also lose. Okay. So now when the message signal you will apply, the carrier amplitude, here you can see the carrier amplitude was between the plus AC and the minus AC. But now when you apply the message signal at t is equal to 0, okay, and t is equal to 0, then it is changing the amplitude according to the message signal. Here you can see the change in the amplitude of the carrier signal. Initially, the message signal amplitude is increasing, hence the carrier amplitude is also increasing, and as the message signal is decreasing, the carrier amplitude is also decreasing. Hence, we can say that the amplitude of the carrier signal is changing. So, if the amplitude of the carrier signal is changing according to the message signal, it is called as the amplitude modulation. And when you connect the peak value of the modulated signal, you get the envelope of the AM signal. And this is nothing but a modulated carrier signal. Here it is written carrier, but better to say it is a modulated carrier signal. The black one is nothing but the modulated carrier signal. Before t equal to 0, it was unmodulated carrier signal, but after t equal to 0, when the message signal is applied, the amplitude is changed according to the message signal, hence it is a modulated carrier signal. And the trapezoidal pattern you can also draw. This is the trapezoidal pattern. How to draw the trapezoidal? So take the maximum value of envelope in the positive side, take the minimum value of the, or you can say the maximum value of the envelope in the negative side, and similarly you take the negative value in the positive side and the minimum value in the negative side, and if you connect these two, and if you connect the both maximum value, then you will get 2 vertical lines, and then join them in the positive side, positive maximum envelope and the positive minimum envelope. Similarly, in the negative side, negative minimum envelope and negative maximum envelope. If you will join it, it will take the shape of trapezoid, and the trapezoid by the trapezoid you can also calculate the modulation index. By the trapezoidal pattern you can get the modulation index, and that is given by L1 minus L2 divided by L1 plus L2. L1 is the broader dimension of the trapezoid and L2 is the shorter dimension. A double student can also attend, no issue. If you are preparing for ESE and if you have prepared once for the communication, if you have prepared once communication for the ESE, then you can also attend. So, what will be the effect of modulation index in the shape of the envelope? So, here you can see we have the carrier signal. When there is a no modulation, we have the carrier signal because the modulation index is 0. We start increasing the modulation index. So when the MA is equal to 0.3, there is a very small change in the envelope, right? There is a very small change in the envelope. When I increase the modulation index more, then there is a good change in the amplitude. There is a significant change in the amplitude. And when you increase the modulation index, you can see that the envelope is shifting towards the time axis, that is 0. Here you can see the minimum envelope is 0.7 AC. The modulation index was less. When I take the modulation index 0.8, the minimum envelope is 0.2 AC. So it is now decreased. That means the envelope is shifting towards the 0. And when I take the modulation index equal to 1, the minimum envelope has touched to the value 0. So it has touched to the value 0 for MA equal to 1, and even I increase the modulation index greater than 1, then the envelope will go in the negative side. It will go here in the negative side, and when it goes into the negative side, it is known as over modulated. It is known as over modulated. So whenever the modulation index is greater than 1, we call it as the over modulated. Whenever the modulation index is less than 1, we call it as under modulated. And whenever there is an over modulated AM signal, in the zero crossing we get the phase reversal here and here. You can see these 2 points. Here the phase is changing. So if the phase has 180-degree shift, then it is known as phase reversal. It is known as phase reversal. So this is the major drawback of having the modulation index greater than 1, because with the modulation index greater than 1, we cannot recover the amplitude modulated signal with the help of envelope detector, because the envelope is going in the negative side. This is nothing but the negative side, right? This is nothing but the negative side. This is envelope in the negative side. So this negative part, this is negative envelope. This negative part cannot be detected by the envelope detector. Hence, we don't prefer modulation index greater than 1. Now, what will happen if the message signal amplitudes are not equal in the positive and in the negative side, like this? Because we know that if I take the sinusoidal signal, then the peak value will be AC and minus AC for the carrier signal. So it will have the same magnitude in the positive side and in the negative side. Okay. See, if I have the sinusoidal signal like this, if I have the sinusoidal message signal like this, then we will have the positive amplitude AM and negative amplitude minus AM. And for this type of message signal, I take the modulation index as maximum value of envelope minus minimum value of envelope divided by maximum value of envelope plus minimum value of envelope. Okay, but when the message signal is not have the same magnitude in the positive and in the negative side, like this. Suppose I am taking some square wave and this is your message signal, and the maximum value is suppose here AM and the minimum value is, they are taking Vmax, so let's take the Vmax. Let's take this as a Vmax. The message signal have non-offset such that its maximum value Vmax and its minimum value Vmin, which are not symmetric. You can see that this is having the higher amplitude, let us say this is 5 volt, and this is minus 7 volt. Okay. So have you got this point? Then they are not symmetric. Vmax is not equal to minus of Vmin. Vmax is not equal to minus of Vmin. So if this is the case, Vmin is not equal to minus of Vmax or vice versa, the modulation index we cannot calculate directly by this formula. Okay, this formula cannot be applied if the message signal has unequal amplitude in the positive and in the negative side. So what we have to apply? We have to apply this formula. Vmax minus Vmin divided by Vmax plus Vmin, same as this one, but plus 2 AC you have to add. Plus 2 AC also you have to add. So have you noted this point? Okay. So if the amplitude of message signal are not equal in the positive and in the negative side, then you cannot blindly apply the formula of modulation index Emax minus Emin divided by Emax plus Emin, because when there is a change in the plus and minus amplitude, positive amplitude and negative amplitude, or you can simply say non-zero offset, if there is a non-zero offset, then we have to take the effect of carrier, that is 2AC. So this is a new formula maybe for you. So all of you please note it down, that modulation index will be Vmax minus Vmin, which is the amplitude of the message signals, divided by 2AC plus Vmax plus Vmin. Next is frequency domain representation. So this is the single tone sinusoidal signal, which is AC 1 plus K mt cos omega Ct cos omega mt and cos omega Ct. And when we open it, this is AC cos omega Ct and AC Ma by Ma into AC here, Ma into AC cos omega mt into cos omega ct, and then when we expand it, cos a cos b, so this is 2 cos a cos b, cos a plus b and cos a minus b. So here we will get the carrier signal. Okay, here it is a carrier signal because it has only the carrier frequency. This is known as lower sideband and this is known as upper sideband. Okay. So in the amplitude modulation signal, we have the carrier component, we have the upper sideband. Upper sideband are the terms which are higher than the carrier frequency, and then the lower sideband which is lower than the carrier frequency. So this is Fc plus Fm, which is higher than carrier frequency. This is Fc minus Fm, and if I calculate the bandwidth, so bandwidth of AM is 2 Fm. Bandwidth of AM is 2 Fm. So is it clear up to this point? Now the power required, how to calculate the power required of AM? So if you want to transmit the amplitude modulated signal, okay, if you want to transmit amplitude modulated signal, that means you have to transmit all the three components. You have to transmit the lower sideband, you have to transmit the carrier, you have to transmit the upper sideband. So to transmit all the three components, all the three harmonics, you need a bandwidth of 2 Fm. But how much power you need? So power can be calculated by calculating the power of each term. So power of the carrier, power of the lower sideband, power of the upper sideband. So carrier is given by AC square by 2. You can write 2R. Okay, AC square by 2R also you can write, and if it is not given, then take R is equal to 1 ohm. Okay, so AC square by 2, total sideband power is the sum of the upper sideband power and the lower sideband power, which is PC MA square by 2, and the carrier power plus total sideband power is PC 1 plus MA square by 2. So PC 1 plus MA square by 2 is the total power required to transmit the AM signal. To transmit the AM signal, you need a total power is equal to PC 1 plus MA square by 2. So power required to transmit AM signal, and here we have transmission efficiency. Transmission efficiency is nothing but the ratio of useful power divided by total power. Useful power divided by total power, PSB upon PT. Here eta is equal to MA square upon 2 plus MA square for sinusoidal signal. For a square wave signal, we say MA square upon 1 plus MA square, and for the triangular signal, we get MA square upon 3 plus MA square. So this is the ratio, and there is one more important point, that the total sideband power divided by carrier power is equal to MA square by 2 for sinusoidal signal. This is ma square by 2, and in general, what we say, in general the sideband power divided by carrier power is directly proportional to square of modulation index. Okay, so square of modulation index, this is directly proportional to square of modulation index. So now, in general, s of t is equal to ac1 plus k mt cos 2 pi fct. So suppose this we have calculated for the sinusoidal signal, square wave or triangular signal. If you want to calculate for the general message signal, where the message signal is other than the square, triangular and sinusoidal, then you can calculate the total power by adding the carrier power, which is AC square by 2, and sideband power, which is AC square k square m square t bar divided by 2. This m square t bar represents the mean square value of message signal. M square t bar represents the mean square value of message signal. Okay, this is the mean square value of message signal. So this mean square value you can substitute here to get the total power. So total power is equal to AC square by 2 1 plus K square mean square value, and this can also be written as PC. AC square by 2 is PC. So PT is equal to PC 1 plus K square m square T bar. So whenever you have the message signal in the form of some random variable, sometimes they will give you the message signal in the form of a random variable. So for a random variable, we can calculate the mean square value and substitute the mean square value here and compare with the standard equation to get the value of K, and you will get the total power. Similarly, the transmission efficiency also you can calculate, which is K square into mean square value of message signal divided by 1 plus K square m square T bar. So this is again an important formula, because the general transmission efficiency they have asked many times in the GATE examination, but they have not asked transmission efficiency single time for the general message signal, which is other than sinusoidal, square and triangular. Okay, so they can give you some random variable and they will say the message signal is defined by that random variable. So for the random variable, we know how to calculate the mean square value, and if you don't know, attend the tomorrow session, because in the tomorrow session we will revise the random variable and the random process. So then you will learn how to calculate the mean square value, and after calculating the mean square value, you can compare with the standard equation to calculate the value of Ka and then substitute it here. For the multitone, the formula of the total power for the sinusoidal signal is same, which is Pc 1 plus Ma square upon 2, something like that. But the difference is Ma square, instead of Ma square we have Ma total square. That means we are calculating the overall modulation index. In the multitone, we have more than one frequency component. So for each frequency, you will have modulation index. So for the frequency F1, you will have the modulation index MA1. For the frequency component F2, you will have the modulation index MA2. So calculate the modulation index for each frequency component, and then you can calculate MA square total by taking root over of Ma1 square, Ma2 square and so on up to Man square. And once you calculate the total modulation index, you will substitute it in the formula of the total power, which is PC 1 plus Ma square by 2, and also for the transmission efficiency, which is Ma square upon 2 plus Ma square. So these two formula you can apply. And because we are discussing about the multitone, so in the multitone we can have the bandwidth which is 2 times of maximum frequency in the message signal. So bandwidth in case of multitone for AM signal is twice of maximum frequency present in the message signal, because in the multitone message signal will have more than one frequency component. It will have 5 kilohertz, 10 kilohertz, 50 kilohertz, something like that, and out of this 5, 10 and 15 you have to find which is the maximum. Obviously it is 15. 15 into 2, that is 30, equal to the bandwidth of the AM signal. Now next is types of amplitude modulation. So we have designed two sidebands and the carrier. So now we have to suppress the carrier signal, because basically the carrier is a waste of power, because in the carrier signal our message signal doesn't lie. So we don't want to transmit the carrier signal. So that is why we will suppress the carrier signal, and when we suppress the carrier signal, it is known as double sideband suppressed carrier. So here you can see that in the FC there is no frequency component present. Okay, in the FC there is no frequency component present, hence it is a double sideband suppressed carrier. The bandwidth for the double sideband suppressed carrier, is twice of FM. Bandwidth for double sideband suppressed carrier is twice of FM. Now the single sideband is one in which we transmit only one sideband and we suppress the carrier component and one of the sideband, because we had the two sideband. So now we have to suppress the carrier as well as one of the sideband. So suppose in this diagram I have suppressed the lower sideband, so we will have only one sideband, which is the upper sideband. So that is why its name is single sideband suppressed carrier. The bandwidth for the single sideband suppressed carrier is FM. The bandwidth is FM. Now we will have the vestigial sideband. So in the vestigial sideband, one sideband is transmitted completely and some part of other sideband is transmitted, which is known as vestige. So we are transmitting one sideband fully. That means we will be utilizing the full bandwidth FM and some part of other sideband. So that small part is given by epsilon. So this difference is given by epsilon. Hence the total bandwidth is given by FM plus epsilon. So this is the bandwidth of VSB. So this is the bandwidth of VSB. So what is the order of the bandwidth in the AM system, which will take maximum bandwidth? So the maximum bandwidth is taken by double sideband full carrier and along with the double sideband suppressed carrier. Double sideband full carrier and double sideband suppressed carrier will take maximum bandwidth, which is 2 FM. Then we have the vestigial sideband, which will take FM plus epsilon, and the SSB-SC will have the smallest bandwidth. How do we suppress the carrier? To suppress the carrier, we actually have different techniques which are known as balance modulator, which are known as ring modulator, that we will discuss. So percentage power saving, which is again an important one. Percentage power saving is an important formula. So percentage power saving is the power saved divided by total power. So how much power you are saving? So in the double sideband, by suppressing the carrier, we are saving the power. So it is nothing but the ratio of double sideband suppressed carrier. It will be the ratio of carrier power divided by total power multiplied by 100. For sinusoidal signal, it is 2 upon 2 plus NA square. For single sideband suppressed carrier, by suppressing one of the sideband and carrier, we are saving the power. So it is nothing but the carrier power plus any of the sideband, like upper sideband power or lower sideband power. You can suppress any one of the sideband. Either you take upper sideband or you take lower sideband, then divide it by total power and multiply by 100, you will get the percentage power saving. So order of power saving, because you can see that single sideband suppressed carrier, you have suppressed the carrier, you have suppressed the one sideband, it will take minimum power. Then vestigial sideband, then double sideband suppressed carrier, because you have suppressed the carrier. And in the amplitude modulation, that means double sideband plus carrier. So amplitude modulation means double sideband plus carrier or double sideband full carrier. So you are not suppressing any sideband and carrier. So that is why it will take maximum power. So this is the order of the power. Sometimes in the examination you will see the question from the order of the power or order of the bandwidth. Now coming to the generation. So there are two methods to generate the amplitude modulation. First is square law modulation. In the square law modulation, we take the message and the carrier, we add them together, then pass it through the nonlinear device. So we will pass it through the nonlinear device. This nonlinear device has characteristics which will be given to you in the examination. This will be the output and input characteristics. Okay, non-linear device will have the characteristics which is nothing but the relation between the output and the input. So output and input V naught and Vi, this relationship we are taking as an standard. So V naught T and VIT are related by this equation. This equation will be given to you in the examination. It will always be given to you in the examination, and then you have to solve by putting the value of Vi. So how do you get the Vi? You will get the Vi by adding the message and the carrier. So whatever message signal is given to you, carrier signal is given to you, add them and then substitute in the given equation of the nonlinear device. You will get the output. So at the output you have to find the frequency. Okay, find the frequency. What are the frequency component present in this V naught? Find those frequency and then pass it through the appropriate band pass filter. So pass through the appropriate band pass filter. So this appropriate band pass filter, this appropriate band pass filter. So after passing through the band pass filter, we will get the AM signal, which is AC A1 1 plus 2A2 by A1 MT cos omega CT. So by if I compare with the standard equation, then we get the K is equal to 2A2 by A1, okay, and the carrier amplitude as AC into A1. Carrier amplitude is AC into A1. So if I take the Fourier transform of V naught T, that is the find the frequency, we need to draw the spectrum. So the spectrum will look like this, and in the spectrum we observe that to have the amplitude modulated signal correctly without overlapping, to have this lower sideband, upper sideband and the carrier, to have this upper sideband, lower sideband and the carrier, we have to use the appropriate band pass filter, and in such a way that it should not overlap with the 2FM. So this FC minus FM should not overlap with the 2FM, and for that we need to take the condition that we need to take this condition. I am writing here Fc minus Fm should be greater than 2Fm. So you will get Fc greater than 3Fm. So you will get Fc greater than 3Fm. So this will be the condition which is written in the bottom. For proper modulation of AM signal, the carrier frequency is Fc greater than 3Fm. Now switching modulator, then in the switching modulator also we use the nonlinear characteristics, or you can say the on-off characteristics of the diode, and by the help of the diode we generate the V2T, and this V2T will again pass through the appropriate band pass filter and we will generate the amplitude modulated signal at the output. Okay, so this is the switching modulator. Because this is something which is having more derivation, I am just telling you the techniques, because it is not having some standard formula. From there they will ask the question in the GATE examination, so you don't need to bother about the formulas of the switching modulator and the square law modulator. You just need to learn the how to analyze the square law modulator blocks. As I told you, you have to add, you have to pass it through the nonlinear device, and after passing through the nonlinear device you will get some output. And because whenever you are passing some signal through the filter, you have to calculate the frequency of the signal which is input to the filter. So whenever there is a filter, you have to calculate the frequency at the input of filter, and to calculate the frequency at the input of the filter you have to take the Fourier transform. So whenever we take the Fourier transform, we get the complete idea about the frequency component present. Like suppose we got some term in the switching modulator, I calculated its Fourier transform, I came to know that it has frequency FM, it has frequency Fc minus Fm to Fc plus Fm, it has frequency carrier frequency, it has 2 times of Fc, it has 3 Fc minus Fm, it has 3 Fc plus Fm. So these number of frequency are at the input of the band pass filter. So how I came to know? When I took the Fourier transform. So whenever you want to pass some signal through the filter, always look for the frequency at the input of the filter, and to calculate those frequency take the Fourier transform. Now let's come into the demodulation of AM. So to demodulate the AM signal, we have one method which is square law, but this time it is demodulator. Remember that the characteristics of nonlinear device will almost same here also, but the important point between the modulation and the demodulation is when we perform the modulation, it is a band pass signal. So that is why we use the band pass filter, and whenever we perform the demodulation, we convert our high frequency signal back to the original signal, and our original signal was low frequency signal. So you are converting your high frequency signal to the low frequency signal. That means you have to use the low pass filter at the receiver end. So we have the low pass filter at the receiver end, and the condition to have the proper message signal at the output of the square law demodulator is the modulation index should be very less than 2. This KMT mod is nothing but a modulation index. So modulation index should be very less than 2. This is the condition has to be satisfied if you want to use square law demodulator. Now we have the envelope detector. The envelope detector has the diode and the RC circuit. Okay, so this is the diode and this is the RC. For proper demodulation using the envelope detector, the value of the time constant is the value of the time constant should always be in between 1 upon Fc to 1 upon Fm, or 1 upon Rc should be greater than equal to Ma into omega m divided by root over Ma square, root over 1 minus Ma square. For multi-tone signal, this message signal frequency will be the highest frequency component. Now, how to avoid the diagonal clipping? When the diagonal clipping occurs, when the diagonal clipping occurs, when the time constant is very high, it is higher than the time period of your message signal. If the time constant of the circuit is higher than the time period of your message signal, it actually clips the peak value of the envelope. So if it misses the peak value of the envelope, this effect is known as diagonal clipping. So that is why to avoid the diagonal clipping, the time constant is to be less than 1 upon Fm, that is the time period of message signal. So to avoid the diagonal clipping, the time constant of the circuit RC should always be less than 1 upon Fm, less than 1 upon Fm. Now, this is the condition to avoid the diagonal clipping. If RC is too large, means when the diagonal clipping occurs, when the RC is too large, as I said, it misses these peak values. It is missing the peak values of this envelope, and that is why we are calling it as a diagonal clipping. And this when it occurs when the RC is too large, even greater than 1 upon Fm, even greater than 1 upon Fm, then the diagonal clipping occurs. So to condition to avoid is RC less than 1 upon Fm, that we have written already. Next, what will happen when we give these inputs to the envelope detector? So when we give the sinusoidal signal to the input of the envelope detector, we get the DC signal. Whether we give cos or we give sine, we get the DC signal. Whenever the modulation index is less than 1, it is less than 1. So whenever the modulation index is less than 1 with AC 1 plus K MT cos 2 pi FCT, so we get the output proportional to the message signal. So we will get the output proportional to the message signal. And when we give the AC 1 plus K MT, that is our AM signal, with the modulation index greater than 1, so for over modulation, envelope detector does not perform well, and it will give you whatever envelope of the input signal is there, it will give you. So the envelope of this AC 1 plus K MT, so this is the envelope AC 1 plus K MT, so it will give you the magnitude of AC 1 plus K MT. So the negative part will also be taken as positive because the diode based circuit is envelope detector, and if there is a diode, the diode will work only in the positive half cycle of the input, so it will give you only the positive value. So that is why we will take magnitude. Now we have the generation of the double sideband. To generate the double sideband, we have two methods. First is balance modulator. Second is your ring modulator. In the balance modulator, we have the two amplitude modulator, and one is AC cos omega ct and another is AC cos omega ct. But here the message signal is 180 degrees shifted. So this is not important. The balance modulator inside block diagram is not important. You know how to analyze it. So again, there is no formula, so I am skipping this part. And ring modulator is important because ring in the ring modulator, the diode is formed in the form of a ring. First thing. Second, the carrier signal is given as a square wave. Usually in the ring modulator, the carrier signal is taken as the square wave, and when that is square wave and your message signal is multiplied, you get some frequency at the input of the band pass filter. Again, by using the appropriate band pass filter, you get the double sideband suppressed carrier. Thank you, Bhaskar. Thank you so much. Thank you so much. So this is your message signal, which is a sinusoidal signal, and as I said, in the ring modulator most of the time, because in every textbook they have taken the carrier signal as a square wave. So this square wave and the message signals are multiplied together in the ring modulator, and here you can see that whenever the message signal is crossing the zero, you have the 180 degree phase shift here also. This message signal, when it will cross the zero, it will have the 180 degree phase shift. So in the double sideband suppressed carrier also we have the phase reversal. Okay, so this is the positive side, this is also positive, so this positive will multiply, you will get positive. When it is negative and you are multiplying this positive side of the message signal, this positive negative will become negative, so that is why this multiplied signal is negative, and so on you can draw. So when the message signal will cross the zero, you will see that it is having the 180 degree phase shift here also. So the double sideband suppressed carrier signal will also have 180 degree phase shift. Now, to demodulate the signal, we have only one method. To demodulate the double sideband, we have only one method, which is synchronous detector. And synchronous detector is nothing but the balance modulator followed by low pass filter. This balance modulator will have the input. One is the double sideband suppressed carrier, and another is the carrier signal, which should have the same carrier frequency which we used in the transmitter. That is why its name is given as synchronous, because the carrier frequency of the transmitter should be synchronized, and we should also generate the same carrier frequency at the receiver. So this is the 2 pi FCT, and we will get the VT and then low pass filter. When you pass it to the low pass filter, the low pass filter will have the cutoff frequency equal to message signal frequency. You will get the message signal. See that triangular signal we usually don't take, because if you take the periodic component of this triangular signal, it will generate, if you take the Fourier transform, it will give you the sync pulse, and this sync pulse will have the number of frequency components and harmonics, so it will not be preferred. Okay, it will become bit difficult to analyze. How low pass filter get enveloped? Here the low pass filter will not get enveloped. Here the low pass filter will get you the message signal only, because when you multiply these two, okay, so this Vt is equal to mt, and then when you multiply you will get cos square omega ct. So this is mt by 2 1 plus cos 2 omega ct. So you have the two components, one is mt by 2 and another is mt cos of 2 omega ct divided by 2. So if you have these two components, so one is having the frequency component fm and another is having the frequency component 2fc plus minus fm. So this low pass filter, which is having the cutoff frequency fm, will pass only the first component, it will reject the second component. So in this way we say that it will have the mt by 2. Okay, so phase shift in the carrier. if there is a phase shift in the carrier, suppose your carrier is not properly synchronized. As I told you that in the synchronous detector, your carrier frequency should be synchronized. So suppose your carrier frequency is not synchronized and it is having some phase error. So suppose the phase error is theta. So with the value theta, if you solve in the same way as I did in the last slide, so this mt cos omega ct and mt cos this is cos omega ct plus theta and mt cos omega ct is multiplied, then you will get the output as mt by 2 cos theta, mt by 2 cos theta. So this, if theta is equal to 90 degree, then the output will be 0, then the output of low pass filter will be 0, and this effect is known as quadrature null effect. Okay, this effect is known as quadrature null effect. Okay, so this is the important effect which can be asked in any exam, like in the PSU as well as in the GATE. So mt cos omega t. Okay, so filter method means here is to generate the single sideband. So to generate the single sideband suppressed carrier, we have three methods. First is your filter method, second is your phase shift method, which is a standard method, third is the Weaver's method. So filter method is very basic, very simple concept. Generate the double sideband. How to generate the double sideband? With the help of balance modulator, and then suppress one of the sideband. How to suppress? Only pass the desired sideband. We have the two sideband in the double sideband. One is lower sideband, other is upper sideband. Which sideband you want to pass? Just keep your band pass filter in such a way that it will only pass the high frequency, it will only pass the upper sideband, or it will only pass the lower sideband. So in this way you will get the band pass. So this is the single sideband suppressed carrier. So generation of the single sideband, the phase shift method we use, and here we have the two balance modulator, two Hilbert transformer, and in the first balance modulator we pass the message signal and the carrier signal directly. In the second balance modulator we will take the Hilbert transform of message and the carrier signal and then give input to the balance modulator, and after that we will get the single sideband. So here you should not go into the analysis. Here you should only know for the name of the method, because remaining part you can do. Here it is a formula session, so we have to focus on the formula, where we are getting the formula. Okay, so this is the Weaver's method, and in the Weaver's method, remember that here according to this side, in the second part of this block, according to this fc plus omega, if suppose you take fc plus omega here, then it will give you the upper sideband, and if you take the fc minus omega here, fc minus omega, then it will give you the lower sideband. So this is the main thing which you should know about the Weaver's method. The block diagram they will give you, but to identify whether it will give you the lower sideband or the upper sideband, just to see the second part of the Weaver's method, where the balance modulator has input which can be the plus or minus with the carrier frequency. So according to this you can decide what is going to generate, whether it is going to generate the upper sideband or the lower sideband. Now Hilbert transform, as we use the Hilbert transform, so Hilbert transform is very important. Hilbert transform does not change the domain. So if your signal is in the time domain, when you take the Hilbert transform, you will get the signal in the time domain only. Hilbert transform is a linear and non-causal system. So how to get the Hilbert transform? If you shift the phase of a signal by minus 90 degree. Okay, if you shift the phase, if you shift the phase by minus pi by 2, this is minus pi by 2. Okay, so if we delay the phase of every component of a signal by minus pi by 2 without changing its amplitude, if you change only the phase by minus 90 degree, then you will get the Hilbert transform of the signal. So Hilbert transform you can calculate directly by the frequency domain also. So to calculate it from the frequency domain, you have to multiply the Fourier transform of the signal for which you want to calculate the Hilbert transform by minus j signum f, or you can also take the convolution of the signal with the 1 upon pi t, which is here. x of t, if you want to calculate the Hilbert transform of xt, then x cap t will be equal to xt convolved with 1 upon pi t. The difference between the Hilbert transform and the Fourier transform is main that only that in the Fourier transform, when you take the Fourier transform of any signal, you get the equivalent signal of the signal for which you calculated the Fourier transform. Let me say it again. In the Fourier transform, when you take the Fourier transform of any signal, you get the equivalent representation but in the different domain. So whenever you take the Fourier transform of suppose sine omega naught t, you get 1 upon 2 j delta f minus f naught minus delta f plus f naught. Okay, so it means that it is changing the domain. This is time domain, this is frequency domain. So it is changing the domain, but both are the same signal. Sine omega naught t and the impulse which I have written in the right hand side, both are the same signal, but they have represented in the different domain. But in the Hilbert transform, both will be different signal because it is not changing its domain. Suppose I calculate the Hilbert transform of sine omega naught t. So how to calculate the Hilbert transform? To calculate the Hilbert transform, as we have written in the third point, that you have to shift it by minus 90 degree, minus pi by 2. So if you will shift it, you will get minus cos omega naught t. Okay, so this sine omega naught t has Hilbert transform cos omega naught t. Both are in the time domain, but whether the sine omega naught t and the cos omega naught t are the same signal? No, these two are the different signal. So here the signal is different, but the domain is same. Both are in the time domain. In the other transform, not only in the Fourier transform, in the Z transform, in the Laplace transform also, the signal is not changed, but the domain changes. Okay. Now next is the property of Hilbert transform. This is very important, Hilbert transform property. When you take the Hilbert transform of any signal, then the signal and its Hilbert transform are orthogonal to each other. When you take the Hilbert transform of any signal twice, because if I take the Hilbert transform, it is a minus 90 degree phase shift. So if I take the Hilbert transform twice, then I will get minus 180 degree phase shift. So this is x double cap t is equal to xt with minus sign. Hilbert transform of even signal is odd and odd signal is even. If I take the Hilbert transform of any signal, then the energy does not change. So energy of the signal is equal to energy content of the Hilbert transform. Fifth point is Hilbert transform of derivative of any signal. So if you want to calculate the Hilbert transform of derivative of any signal. So this is the derivative of the signal, and if you want to calculate Hilbert transform, then what you can do is you can first calculate its Hilbert transform. First calculate the Hilbert transform and then you can differentiate. So after calculating the Hilbert transform, I can differentiate if I want to calculate the Hilbert transform of differentiated signal. And last is a signal and its Hilbert transform has the same autocorrelation also. So Hilbert transform and its the signal and its Hilbert transform will have the same autocorrelation. So this is the frequency division multiplexing block diagram, and we just need to focus on the bandwidth. Bandwidth of frequency division multiplexed signal is n times of fm plus n minus 1 times of f guard band. N minus 1 times of guard band. If all the message signals, this first message signal, this second message signal and nth message signal all are having the same frequency, then the bandwidth of the frequency division multiplexed signal is given by this formula. So this formula is important, as per the exam point of view. Next is a pre-envelope. Pre-envelope is nothing but the GT. The pre-envelope of any signal is G plus T, and it is equal to GT plus J into G cap T. So GT is your band pass signal and G cap T is Hilbert transform, means any signal, and G cap T is a Hilbert transform. So if you represent the signal with its Hilbert transform in the complex form, then you will get the pre-envelope. And with the help of pre-envelope, you can define the complex envelope as well. So any band pass signal, okay, let me write here, any band pass signal can be represented in the form of in phase component and the quadrature component, right? SIT cos omega CT minus SQT quadrature component and sin omega CT. Any band pass signal can be represented by this. So if S of t is a band pass signal, then it can be represented by this one, and the complex envelope. The complex envelope of this band pass signal is also given by SIT plus J into SQT. Okay, this will be your complex envelope. If we have 3 low pass filter and 3 band pass filter, it will which will FDM is not necessary to have 3 band pass filter. It is a n number of band pass filter and n number of low pass filter. Okay, here you can see we have n number of message signal. So if you have the n number of message signal, then it has the n band pass filter and n low pass filter. Okay. Autocorrelation, you will understand tomorrow when we will discuss about the random variables. So now we will have the angle modulation. So in the angle modulation, we will be having S of t is equal to AC cos omega ct. AC cos omega ct plus phi t is the original form of angle modulation. So how to calculate the instantaneous frequency? You have to take the angle and then differentiate it. So to calculate the instantaneous frequency, Fi is equal to Fc plus 1 upon 2 pi d phi by dt, and the frequency deviation is nothing but the instantaneous frequency minus carrier frequency. The frequency deviation is given by instantaneous frequency minus carrier frequency, and the peak frequency deviation can also be calculated as 1 upon 2 pi maximum value of d phi by dt. 1 upon 2 pi maximum value of d phi by dt. So these are the formulas for the any angle modulated signal. Okay. Next is phase deviation. Peak phase deviation is nothing but the maximum value of phase which is given by the difference between the unmodulated carrier phase and the modulated carrier phase. So the difference in the phase of the modulated and the unmodulated carrier. Phase modulation is nothing but when the phase of the carrier varies according to the message signal. So phi t is equal to mt, then we call it as a phase modulation. So phi t is equal to kp mt. This is the constant. Okay, this is your phase constant, right? Phase sensitivity of the modulator, and mt is equal to am cos 2 pi fmt. So this is ac cos 2 pi fct plus kpmt, and mt is equal to am cos 2 pi fmt, right? Next is when for the phase modulated signal, what is the expression? The expression for the phase modulated signal is ac cos omega ct plus beta p, and beta p is the modulation index, so it is kp into am, and maximum frequency deviation is equal to kp upon 2 pi maximum value of dmt upon dt. So we have to substitute in the phi is equal to kpmt. You will get the frequency deviation. And for the sinusoidal signal, this mt is am cos omega mt. So when you substitute and when you take after getting the maximum value, you have to take the magnitude also. So when you differentiate and then take mod, here you will see this kp am fm. So what it shows? It shows that the frequency deviation delta f depends on am and fm. In case of PM, modulation index is given by the maximum frequency deviation and the massive signal frequency. The maximum phase deviation is maximum value of phase. Phase is kpmt. This is mt is equal to sinusoidal, then kpam. So this is for the sinusoidal. Now coming to the frequency modulation. In the frequency modulation, the delta f is proportional to the message signal. The delta f is proportional to the message signal, and delta f is given by 1 upon 2 pi d phi by dt. So what is the difference between the phase modulation and the frequency modulation? The main difference between the phase modulation and the frequency modulation is in the expression. In the frequency modulated signal, we have the message signal in the integrated form. This is in the integrated form. On the other hand, in case of PM, we have the direct form. So we had the AC cos of omega CT plus Kp into Mt. This was your expression of the PM signal. This is case of PM signal. So in PM you have the message signal in the direct form, and here in the message signal you have the integrated form. Okay, so instantaneous frequency is given by Fc plus maximum frequency deviation. Minimum instantaneous frequency is given by Fc minus Fc minus delta F max. So if you will add them, you will get the carrier frequency, which is Fi max plus Fi min divided by 2. Now the carrier swing is nothing but the difference between the maximum instantaneous frequency to the minimum instantaneous frequency. Maximum instantaneous frequency and the minimum instantaneous frequency, and the modulation index is given by delta f divided by fm, which is kf into am. So here you can see that the frequency deviation only depends on here I should write delta f only depends on message signal amplitude. Message signal amplitude. Okay, message signal amplitude. It only depends on message signal amplitude. So what is the expression of the angle modulated signal? In the power, it is AC cos omega CT plus phi. How do you calculate the power of the FM signal or the angle modulated signal? The power is given by AC square by 2. The power is given by AC square by 2. Now what are the types of frequency modulation? Depending on the modulation index, okay, depending on the modulation index, we can categorize into the two parts. One is beta less than 1, another is beta greater than 1. And beta is less than 1, it is known as narrowband signal. What is the difference between the narrowband signal and the narrowband signal and the wideband signal? Modulation index is greater than 1 for wideband and less than for narrowband. What is the difference between the AM and the narrowband? The lower sideband is inverted. Here you can see this is the lower sideband and the lower sideband is inverted. Lower sideband is inverted. Lower sideband is inverted. Okay. Now wideband FM, what is the expression of the wideband FM? In the case of wideband FM, the expression of the signal is S of t is equal to AC summation n equal to minus infinite to infinite j n beta cos 2 pi fc plus nfmt. So these are representing the sidebands. For n equal to 0 we get the carrier signal, for n equal to 1 we get the upper sideband, for n equal to minus 1 we get the lower sideband, and so on. So what are the terms for which we get the carrier frequency 0? Because if I put n equal to 0, we get AC j naught beta and cos omega ct. So this is the carrier component. So to make the carrier component 0, we have to keep the J naught beta 0. So to make carrier component 0, to make the carrier component 0, J naught beta has to be 0. J naught beta should be 0. Okay, so if the J naught beta will be 0, that means this is the first time when the J naught beta is 0, because for n equal to 0 and beta equal to 0, we have the maximum value 1. Then we started increasing the value of beta. We are increasing the value of beta from 0 to 2.4. The Bessel function is decreasing, and it is reaching to the 0 for the first time for beta equal to 2.4. Then after that it is increasing. For the beta equal to 5.45, it is again 0. Then for 8.65 it is coming 0 for the third time, and then 11.6. So these are the values of beta for which the J naught beta is 0. So that is the reason why we take the beta equal to 2.4, 5.5. Now because we have drawn the wideband FM signal, this sideband if you will draw, there are n equal to minus infinite to infinite. So because of that, n is varying from minus infinite to infinite, we have the infinite band. So because of the infinite band, the theoretical bandwidth of FM is given as infinity. But because we cannot have the infinite bandwidth practically, so because of that, we consider the Carlson rule, and according to the Carlson rule, the bandwidth is considered for the 98% of the total power. So if we want to transmit 100% power, we need infinite bandwidth. So we cannot have the infinite bandwidth, that means we cannot transmit 100% power. So how to optimize it? We are actually transmitting the 98% of the power, 98% of the total power, such that the bandwidth is also reduced by the significant amount. So now the bandwidth is given by the Carlson rule, which says that if you are transmitting only the 98% of the total power, then we can have the significant bandwidth, so which is given by 2 times maximum frequency deviation plus FM. Now we have some methods of generation of wideband FM. These are the slope detector, balance modulator, phase discriminator, in which we have Foster-Sillay and the ratio detector, and the third method is known as phase lock loop. So these are the three methods for which we actually use for the generation and the detection of the FM signal. So what are the characteristics of the radio receiver? Now coming to the third part of this overall analog communication, what is the carrier deviation in FM and why it should be high? Carrier deviation. I didn't say anywhere carrier deviation means you want to say frequency deviation. And frequency deviation is usually less. Frequency deviation is usually less. So if we move into the third part of the revision of the analog communication, that is the receiver. So whenever we design the receiver, we should keep some point in our mind that the selectivity of the receiver should be high. What is the selectivity? The selectivity of the receiver is the ability to pick the desired signal, to select the desired signal and reject the unwanted signal. So you don't want noise and any other signal. So you have to select your signal only, means the desired signal only, and reject unwanted signal. Second is the sensitivity. Sensitivity means it is the ability of the receiver to pick the weakest signal. Means weakest signal means the lowest amplitude signal. Okay, the lowest amplitude signal. It is the ability of the receiver to pick the lowest amplitude signal, and once you pick the lowest amplitude signal, you have to amplify it. So that is the sensitivity of the receiver. And fidelity means it is the ability of the receiver to reproduce all the frequency component. It is the ability of the receiver to reproduce all the frequency component present in your message signal, because you cannot recover your frequency at the receiver. You can increase the gain, you can decrease the gain, but you cannot regenerate the frequency by your own. So your receiver should be capable enough to retrieve all the frequency component present in your message signal, and that is what the parameter defined by the fidelity. Okay, the parameter fidelity defines that only. So super heterodyne receiver, we have super heterodyne receiver in which we receive the signal from the antenna, then we have the RF stage, and after taking the signal from the RF, we perform the mixing, that is heterodyning. Why its name is heterodyne? Because heterodyning means mixing. So you are mixing the two frequency. One is coming from the RF frequency, RF stage, and another is coming from the local oscillator. So the local oscillator frequency and the RF stage frequency are multiplied. When they are mixed, they are multiplied. Whenever you multiply the two frequency, you get the sum frequency and the difference frequency. Whatever you want, you can take. So we will add and we will subtract that, and we will get the intermediate frequency, and that intermediate frequency we will pass through the IF amplifier, and after that we will demodulate it, demodulation, then audio amplifier, and after that power amplifier. So this is the block diagram, and then we give output to the loudspeaker. We take output from the loudspeaker. And what is the Q factor of a RF stage amplifier? The Q factor of a usually the tune circuit, and for the RF stage is nothing but the center frequency divided by bandwidth. The quality factor should be low, because the quality factor high is not possible to generate because of the hardware limitations. So the main disadvantage of the super heterodyne receiver is the image frequency. The image frequency is given by Fi. The image frequency Fi is equal to Fs plus 2FIF. Fs is the signal frequency. The frequency in which you will tune your radio receiver is the signal frequency, plus 2 into FIF. IF is the intermediate frequency which was input here. This is the intermediate frequency amplifier, and input to this is FIF. So this is FIF. This will be the image frequency if the local oscillator frequency is more than the signal frequency. This is saying that the local oscillator frequency is more than the signal frequency, then we will have the image frequency as Fs plus 2FIF. If the local oscillator frequency is less than the signal frequency, which is Fs minus FIF, then we will have image frequency as Fs minus 2FIF. Okay. So range of the bandwidth of the RF amplifier should be always, the RF amplifier should have the bandwidth in the range of 2 FM and 2 FIF. The bandwidth of the RF amplifier should be in the range of 2 FM to 2 FIF. The image should always be rejected. The image frequency should be rejected at the RF stage itself. Okay. So the image frequency should be rejected at the RF stage. That is why it is sometimes known as pre-selector. Sometimes we call the RF amplifier as a pre-selector, because the image frequency should always be rejected at the RF stage only. The image rejection ratio is given by alpha, which is equal to root over 1 plus q square and rho square, that is equal to gain at signal frequency divided by gain at image frequency. The gain at signal frequency, the gain at signal frequency, and gain at RF frequency. The gain at signal frequency divided by gain at gain at the RF frequency divided by gain at image frequency. So gain at image frequency is gain Fi, and gain Fs is the signal frequency. And how do you calculate the rho? Rho is the F image divided by Fs minus Fs divided by F image. Okay. So this is it. These are the formula. Yes, Ravi, the formula, this PDF I will make available in the my Telegram group, okay, my Telegram as well as in the WhatsApp group also. Yes, Devashish Pradhan, we will connect very soon in the digital board. Okay, in the digital board also we will connect. So I will share the PDF in the my WhatsApp group as well as in the I will share the PDF in the Telegram group of the BYJU'S exam prep English channel. Okay, what is the channel? I think you know about the Telegram group of the BYJU'S exam prep, so you can just have that. So all of you are subscribed to the BYJU'S exam prep channel, right? The Telegram group of the BYJU'S exam prep. So I will share the PDF in both the group. One is our personal WhatsApp group, and the WhatsApp group is bit personal. It is only for the vision batch. I cannot share it here, and I will share my you can subscribe or you can join the group Telegram group which is given in the description. I guess in the description there will be a link of the Telegram, and also in you can see in the pin comment also, the pin comment is also there. Chinmay, the pin comment is also there. Chinmay Roy, okay, and I am sharing you the my Telegram group also. Okay, let me show you that my Telegram group is this one, communication and EMT, okay, by Sakit sir. You can see here, you can search it here, okay, communication and EMT in bracket Sakit sir. This is the Telegram group, and this is t.me/gate underscore Sakit Verma sir, okay. Okay, so you can join this Telegram group, and here I will share the PDF. Here I will share the PDF, and also in the WhatsApp group, and also in the BYJU'S exam prep, which has the Telegram group. In the comment section, in the comment section you can see that group name, and from there you can find the okay round tube. What do you want to ask? That career deviation, the deviation from the career. Okay, so have you all got this group? You should all aware with this Telegram group, because I will be taking the sessions and sharing the PDF in this group as well as in our BYJU'S exam prep group, right? BYJU'S exam prep group, which is in the pin section, comment section. In the pin there is a by the name of BYJU'S exam prep for GATE, BYJU'S exam prep for GATE. Okay, so do subscribe the channel. I hope that this session was useful for all of you. So can you guys comment here, was this session useful for all of you? Was this session useful for all of you? Thank you, Bindu. Thank you, Prasanna. Because this session is mainly for those who have studied once, so that's why I moved a bit faster, because I know that you are aware with the terms and terminology that we are using. In the amplitude modulation I took much time, but for the other topic I took less time, and obviously we all know that amplitude modulation has many topics, so it takes time to complete it. Okay, so if you have studied the digital communication, then you can join me tomorrow also at the same time 6 p.m. Okay, if you have finished the digital communication also, then the tomorrow we will be discussing the random variables. Okay, tomorrow we will be discussing the random variables, random process, and then digital communication. Okay, these three topics we will discuss tomorrow at the same time. Tomorrow at the same time at 6 p.m. Okay, those who have studied the digital communication, okay, this is only for those who have studied the digital communication, because it will be also a bit rapid session, so it is difficult to cover all the topics in a very short way. So I will be discussing the formulas which is useful for the baseband, bandpass, and noise, and which will be useful for the solving the questions. Okay, the time is 6 p.m. only tomorrow at the same time, 6 p.m. Okay, thank you guys for watching this session. I hope that you enjoyed. So don't forget to join this telegram group. Okay, don't forget to join the telegram group, and it's linked group discussion also, so you can post your doubt in this telegram group, and you can ask me doubt there directly. Thank you so much. Good night. Take care and have a nice day. Thank you.